Hi everyone. Hello. Stop talking, Colin. So Tom can't make it today, so I've been nominated. Thank you all for coming. So we've got a talk about the Rust borrow checker by Diogo. So yeah, looking forward to it.
All right. So I'm Diogo. I'm going to talk about this thing called borrow checker, and this is basically the thing that is really unique to Rust. And it is a bit important to understand what's the goal of Rust, because otherwise none of this makes sense, right? Because you have safety with stuff like Java and Scala. But the goal of Rust is a bit different because it wants to be very, very fast and safe. So that means that you don't have like a runtime keeping you in the right place, right? There's no runtime making sure that you use the memory as you should. So it kind of uses a thing called, which I'm going to call compile time memory management. So how can we actually have this and safety? All right. Basically, I'm going to promise you that I'm going to explain these three things about Rust. So why does it need GC? How can it ensure that you are always accessing memory right and you don't like have null pointers exceptions or invalid pointer dereferences or stuff like that? And how this all comes together to actually make sure that your program is data race free. So what is memory safety? It really depends on who you ask, but for these purposes, I'm going to say it's kind of these things and things that are similar to this. So we have buffer overflows and buffer overruns, which basically means that you have like an array and you read past the end or past the beginning of it, read or write, right? And the Rust approach for this is to do dynamic bond checking. And this is the only thing here that is actually gives you a penalty in runtime, because it actually will have to check in runtime that your indexes to the array are correct, right? Now you can have initialized variables, and if you read them, that's bad. You are reading memory that maybe was not cleaned by another thread or by another thing. And you can also have null pointer dereferences. And the Rust approach to this is just don't do that. So you can't do that. All variables must be initialized, and you don't have null pointer dereferences because there are no null pointers. Okay, you don't have a null. And then there's these things related with memory allocation, and in this case, freeing the memory, right? If you coded in C or C++, you'll probably already met some of these. If you free something twice, you'll get a problem. If you free something that was not allocated, you'll get a problem. So the Rust approach to this is Rust is going to do the memory management for you, but it's going to do it at compile time. So no overhead here. And then there is this dangling pointing dereference, which means that you have a pointer to something that maybe was accessible to you, but now it's not for some reason. And this is the kind of the hard part to fix here, right? The other ones are kind of easy to see how they can be solved, but dangling pointing reference, a little bit harder. And that's basically what the talk is going to be about. So let's look at this piece of C++ code. So we have a vector. Well, let's actually go through it and run it. So this is our call stack. So we don't know who called foo, but whatever it's in the call stack, it's there, right? Sorry. So let's start running this thing. We create a vector here, and the vector in C++ is three things. Maybe it's more, but conceptually it's three things. It's an array. That's going to point to some memory allocated in the heap. It has the length of the array, the number of things that you inserted in it, and it has the capacity of the array, so that you can check if the array is full, it has to expand it, right? So let's run this thing. We push 5 to the stack, to the vector, which means that the vector will allocate an array. It will have size 1, so it will point at this thing that we just inserted. And then we can create a variable and point that to the first element of the array. So this is a reference, right? I'm not actually holding 5, I'm pointing to 5. Now, if I add a new thing to the array, to the vector, it will have to expand, right? Because it doesn't have enough space on it to accommodate for this new element. So it will actually create a new element, create a new array, copy the elements, insert a new one, and it will free the old one. So now we have first pointing at whatever. It's an invalid reference, right? So if you run this next thing where you actually print the value of first, it will blow up. Or maybe even worse, it will not blow up, it will just print the wrong thing, and your system might run for months doing the wrong thing until it's obvious that it's doing the wrong thing. Okay, so this is kind of our motivation to the borrow checker, right? And the thing that is wrong here is that we have mutability and we have aliasing at the same time, right? And that's actually what went wrong. By aliasing, I mean you have two different paths to the same memory location. So you have the vector and you have first pointing at the same stuff, right? And since you have both at the same time, you could change something while something is pointing at it, invalidating that pointer, right? So to talk to you about the borrow system, the first thing you need to know is the concept of ownership. And it's a very natural concept. It's just like you have a book, you look at the book and you think, I don't want to have this. Maybe I'll give this to someone else. And you give that book to someone else, and it's theirs. It's not yours anymore. You can't do things to with it. You just lost it. It belongs to someone else. That person will probably stop smiling because it's a COBOL book. But yeah, it's a very simple concept. So let's look at the code to see how this works. So here we have a function that creates a book, right? Let's create a book on stack. So this is foo, this is the method, and this is the stack frame of that method. So we create a book, and then we call publish, and we give the book, and when we give the book just like this, we are giving ownership away. Let's see what that means. So we push book onto the stack so that we can call the publish method function. And we lost book. In foo, this book here is no longer accessible because we just give it away. That's giving ownership away, right? And now publish can do whatever to the book. It can write or read to it. It's theirs, so it can do whatever. And at the end of publish, when publish returns, it will just destroy the book because since it was their book, it's the responsibility to free it. So what happens if we actually try to reuse it again? We can't, right? It was invalidated. It was freed. Well, if we ask Rust, the Rust compiler, it will tell you, okay, use of moved value book, and it will tell you it was moved there, and you are trying to use it here. That's no good. Okay. So what did we learn? We learned that every data has exactly one owner, and when the owning scope disappears, that thing gets freed, right? So this means receiving by ownership, receiving by move. That's what it's called, like it's move semantics, because it's not copied, it's moved. And the compiler just looks at this and it knows, okay, I'm the owner of this thing. This is where it goes out of scope. I'll just generate the code to free it and to release it and put it in there when I compile, right? And this basically means that we don't need GC, right? It gets more complicated than this, but if nothing breaks from here on, I already showed you how to not have GC in a language, right? So with books that you actually value, you probably don't want to give ownership away, right? The most common thing that you want to do is that you lend it to someone, and that person reads it. Hopefully, it won't write to it. and then it will give you back the book, and everyone is happy, right? So let's see the code. We added this thing here, right? Same code. We added this thing here. We added this %, there as well. And that basically just means that you are receiving it by reference, which means borrowing. And the borrow is immutable, right? By default in Rust, everything is immutable. So let's run this again. We have book on the stack. We call publish. So now we have a reference to the book, but not a copy of the book, just a reference to it. It's just a pointer. Publish can read the book, cannot change it, can read it, and then it returns, and it works. And you can reuse it. It's fine. You can now print the book or whatever you want to do with that. Okay. So how does this work with mutability? What are the rules of what you can do? So let's say we have a book. Let's say we have a book and we want to change it, right? We want to set the title, and maybe we want to set the license to Creative Commons, and maybe we want to fix the typos. So we want to mutate it. How does that play with borrowing it? So we are borrowing here the book to be, and then we are changing the book inside of this, and we are reading the book, right? So if we try to compile this, Rust will tell you that book cannot be borrowed as mutable because it's already borrowed as immutable. So here we are borrowing it immutably to be, and then here we are trying to change the book, but we can't because it's borrowed already to be, right? So in this scope, you cannot change book. You can read B because you have the reference to it, but you can change it. If we delete this thing, this works. So you can read book. That's fine, right? You just cannot change it. So yeah, you cannot mutate while borrowing. So let's now see an example of borrowing it mutably, right? So we have here the mute keyword, which when you apply to in this way, it means I want a mutable reference. So now B is a mutable reference to book. And if you try to compile this thing, it will tell you that you cannot borrow book as immutable because it's borrowed as immutable. Let's see why. So we are borrowing here mutably, and then we modify it, and that's fine because we have a mutable borrow. And then here we are trying to read book, which is borrowed, and we can't. So we cannot read stuff that is mutably borrowed. So if we remove it, the compiler will tell you that everything is fine. And this is the general rule. You cannot access stuff that was mutably borrowed to someone else. So, putting everything together, what did we learn? Cannot mutate while borrowed, cannot access while mutably borrowed, which means this. If we have ownership, that's what it means. If you have ownership of some data, we can mutate it, but we can't have multiple owners, right? We can only have one owner. If we have a reference to some data, you can have multiple references. They are immutable, that's fine, but you cannot change it. And if you have a mutable reference to something, you can only have one, and you can change it, obviously. So this basically means that you can either mutate something or you can share it. You cannot do both at the same time, right? Which was the original problem with our piece of C++ code. This is the exact same thing we saw before. So let's rewrite this in Rust, and this is what it looks like, pretty similar to what we saw. And if we try to compile it, it will tell us that, hey, you can't change the vector, which would cause the array to be freed and moved. because it's borrowed here, so you can change it while it's borrowed. And it even tells you where the scope ends, so meaning that after this you can change it. In this case it's a function, so it doesn't apply, but the thing is, this is basically the rules to have memory safety, but these rules are actually in general make some sense. For instance, here we have something that would not have any problem in terms of memory safety. This is just a piece of Java code, and you are just iterating through a set. And if you use Java before, you probably already tried to do this. So you iterate through it, and at some point you decide to remove something from the vector or add something or whatever. And if you ask Java to compile this, it will tell you it's amazing. And if you actually run it, you'll get one of these, right? Which makes sense because you are iterating through something and you are changing that thing, so your iterator might be completely invalidated by your change. But Java will not do anything to prevent that unless you actually run it. Same code in Rust. We already saw something similar. Inside of this block, set is read-only. So even though you would not have a memory safety problem, this will not compile because it's borrowed there, and Rust will prevent that problem from happening. Okay, let's look at the piece of code that is wrong. This should not compile because we are creating a book, and then we immediately return a reference to that book. This is returning, right? And this cannot work because you create a book, and if you return a reference to it and then your function returns, the book will be cleaned, so that memory would be invalid, right? You can return a pointer to something you just destroyed by the very act of returning. So let's see what Rust has to say. Error, missing lifetime specifier. So, okay, what's a lifetime? And he expects something to be there. Okay. A lifetime is basically this section of code where some value is accessible, right? So here you have book, and during this section of code, book is a thing that you can access, right? So this is the lifetime of book. Well, you might not be able to access it because it might be borrowed or something, but it exists, right? So this is the lifetime of book, and then we borrow it inside of that scope. This is just the scope things, right? So we borrow it, and we can do stuff to it. And this is the scope of the reference to book. So this basically means that what you are doing is valid. And it's valid because the scope of B is included inside the lifetime of book, right? Because otherwise, you would be holding a reference to something that doesn't exist. So this is what lifetime means. Let's kind of just blindly put a lifetime annotation there. This is a lifetime annotation. And let's not really care about what it means right now. Let's just like ask Rust to compile this thing and see what it says. So now it's pleased with the lifetime specifiers, but it will tell you that book does not live long enough, which makes sense. You are returning a reference to something that is going to be destroyed immediately. Okay, so how can we actually use these lifetime annotations to do something useful? So these lifetime annotations are basically a way for you to establish a relationship between two references, right? So we have here a function that receives an array, receives a vector, and it returns a reference to the same element. You are returning a reference, so Rust will not know where that reference comes from, and it needs to know that because it statically needs to keep track of everything, right? So you basically tell him, oh, I'm receiving a vector by reference, and I'm going to return a reference to something that is inside that vector. And now it can check the code that calls this and check that it does the right thing. So let's see a piece of the code that does that. Just creates a vector, pushes something to the vector, gets a reference to the first thing. And because it knows that relationship, it knows that this reference is a borrow of vector, right? Because that's the signature of the function. So the scope of S is contained within the scope of vec, so that's fine. This code compiles. We can also use these lifetime annotations to hold data, right? We can create structs, and those structs can have references to external data. And you annotate it like this, right? Same kind of logic. So let's see an example where we can use this, or where this might be useful. Let's say we have a book that we want to publish in two versions, one for the UK, one for the US. The lines of the book are all the same language, but we want to have different covers because of reasons. So we create two books, and we can just pass a reference to the lines. And this works, right? We can just hold there a reference to these lines, and these are the thing that is actually holding the content of the book. And we can publish, and this basically covers the Rust approach for memory safety, keeping track of all references and enforcing those sets of rules. But in this case, there's something that you might want to do that you can't. Imagine that you want to return those books. Well, you cannot really do that, because if you return from this function, lines will be freed, and lines will be freed, and that means that the book content will be invalid. So you cannot write this. This will not compile. What can you do then? Well, we can, of course, just make the book hold the lines, so it can own them. But if you own the lines, that means that you have to copy them. Let's go through our example. So create lines, it's there. Let's now create the book, the US book. We create the book, but notice that we are cloning the lines. So we are just like copying the whole array and put it in the book. And then we create the UK book, and we can actually move lines there, right? Because we don't need it anymore. So we can actually move lines there, and lines is not accessible now in the function foo, and that's fine. We don't need it. And then we return it. And this works. This is fine, but we are kind of duplicating a whole book, which is wasteful. So how can we kind of share them, but kind of pretend that they own them? Well, you can do that by an abstraction that the standard library gives you, called a reference counting smart pointer. And basically, it works like this. Let's run the code. So create a book. You have book. Put the book inside of a reference counter smart pointer, which means that you move the book. You move the book to it, and because you move it, it's no longer accessible there. And it has also a reference count, which is basically the number of smart pointers pointing at that thing, the number of RC pointers pointing there. And it's going to be 1 because we only have one RC pointer. And then we create another one, and we are cloning it, right? But when we clone it, we are not actually cloning the content of the book. We are just only cloning we are just creating a new reference count pointing at the same thing, right? So it will create this thing, the data will point at the book, and the reference counter will be increased by 1, right? There's 2 things now. Now we can drop stuff. This basically means, okay, I don't want to have this anymore, just release it, and it's obviously no longer accessible. So let's do that. That decreases the reference counter, right, by 1, and it destroys the thing. And now we can print a book too. We still have access to it. It's there. And now we can drop it. And there, basically what's going to happen is the reference counter will decrease the reference counter, and it will know, okay, this reached 0, so that means that no one else has a reference to it, so it's my responsibility to free it. And it does that, right? So, yeah, this is basically a way of you to have multiple ownership without really having it. But of course, you cannot have mutability, right? Also, internally, since you have multiple ownership, which is the mechanism that we use to know when to free the memory, now the RC counter has to basically take care of that. It has to know that it's its own responsibility to free it. So now you might say, okay, but reference count is shared and it's mutable, right? We just saw that when you cloned the reference counter, it increased. So how can this happen? Well, there was one thing that I didn't talk about, which is unsafe blocks. So you can have unsafe code, and in that unsafe code, you can do a lot of things. You can have raw pointers. You can dereference things that are not supposed to be dereferenced. You can relax the borrow system rules to share something and also mutate it. But of course, you have to be very careful when you do this, because if you break things, your code might not work, right? So the idea is that you use these unsafe blocks inside abstractions that are safe from the outside view, like RC. RC, to have that sharing, it has to use this inside of it. But in fact, from the outside perspective, it's all safe. You cannot mess up anything. So, okay, we're going to talk about concurrency now. So this is the definition of data races. It's a bug caused by concurrency access to a shared memory location, of which one of the accessors write to it, right? If you remember what we saw before, this is exactly the same kind of rules that we have in the borrow system. Borrow system just tells you that you can only share or mutate. So, yay, it's done, right? We already enforced this, so we don't have data races. Well, but we still want to share state and mutate it in a safe way, right? And Rust gives you that. So let's write the naive thing and just have a counter, create 5 threads. Each one of them will increase the counter, and then let's pretend that there is code here that's actually going to wait for all the threads to stop. And we'll just print the counter after this. If we do this, we know that this cannot work, right? Because there's no protection at all in the counter variable. So this is not thread safe. So something must be wrong. Let's see what's wrong. So Rust will tell us that the closure might outlive the current function. This thing here is a closure, right? So this is like a lambda function. And it's right. So we are actually waiting for all the threads here. But the threads might live for 60 seconds, right? And the function might return. And if the function returns, counter is destroyed. So we cannot certainly access that in the thread. So that's what Rust is telling us. There is some kind of thing that we need to do to make sure that we can change that thing. So what can we do? We can make all the threads own that data. Because if they own it, it's theirs. No one else can destroy it, right? So we create this. We put it in RC. That's what RC is for, right? It's for having mutable ownership, multiple ownership. So we put it inside RC, and we clone the RC so that we can give away an RC pointer to each of the threads. And we added this keyword here because think inside the closure, they kind of receive them by reference, they borrow it, but we actually want to tell the closure, no, we are actually going to move this thing here, so this is lost from the original thread. Okay, and then we increase the counter this way. Let's see what's wrong here. So Rust tells us that RC cannot safely be transferred between threads. Why is that? Oh, okay. No, sorry. It tells us that it cannot be safely transferred between threads, and it says that it cannot do that because send is not implemented for RC. So what is send? Okay, in Rust there is something called traits, and traits are like type classes. They are exactly type classes. So they can be implemented for types, right? You can have, for instance, traits like clone, which means that something is clonable. But there are these two special traits. And these traits basically have a semantic related with threading. And that's basically the only thing that Rust knows about threading. So when you have a type that implements send, it means that you can move it between threads. Just that. You can just move it. If you have a thing that implements sync, it means that you can share immutably a reference between threads. Okay, so yeah, and these are basically automatic traits. That means that if you have a type that you defined where all the elements are send, then the whole thing will be send as well. Same thing applies to sync. So you can implement them by hand, but that's unsafe. Basically, you are saying, I know that this looks like it might have data races, but I know what I'm doing. So why is RC not thread safe? Well, because the reference counter is written by multiple threads. Is written when you clone it. So that's not thread safe. So you must have something that will give you some synchronization to change that reference count. So you have this atomic reference counter, which has a lock protecting the thing that changes, which is the reference counter. And this works, this implements send, and because of that, we can change the code to atomic reference counting. And now, if we actually try to run this, it will tell us that we cannot immutably borrow C, which makes sense because a reference counter cannot change the thing being referenced. It's only read-only, right? So this is pointing at that 0 that we store there, but we cannot change it without some more trickery, okay? So what can we do? There's a thing called the Mutex in Rust, and it's very easy to use. So you can just put some value inside the Mutex, and when you need to access it, being either reading it or changing it, you need to ask the Mutex for a lock. And this lock will give you a Mutex guard, which basically is the only way that you can access the data through. And when it does this, it also locks the lock. So inside of this scope, the memory is yours. No one else can read it, no one else can write it, right? And when it goes out of scope here, it's going to be automatically unlocked so that other threads can change it. Now you might notice that we are here changing a piece of data, but the mutex doesn't have, is not mutable, right? So how can this be? Well, Mutex basically uses some safe code inside of it to ensure that it looks from the annotation immutable, but it's actually mutable, but it's okay because we are not sharing it, right? Because we have a lock. So it basically uses unsafety to give you this safe abstraction that you can use for multi-thread code. So it gives you multiple writers, but it has to internally make sure that there is no sharing at the same time. Right? So what we need to do, so this is kind of similar to RC. So RC gives you multiple ownership, but since ownership is the thing that Rust uses to release resources, the RC must take care of that. And in the same way, the Mutex gives you internal mutability, but it has to make sure that it actually makes it in a safe way so that no one can write while you read. So this is the final code. We just added the Mutex here and here. And here is the point where we actually unlock the mutex so that we can actually change the value that is inside it. And this works. Compiler is happy. If you actually run this thing, it will give you the right result. It's indeed 5. And yeah, that basically shows you how to have no data races by purely looking at the code statically. And you might say that, okay, we saw a lot of errors today, right? And you will see a lot of errors if you actually start using Rust. So someone on Reddit said, Rust has a very high friction coefficient. And one of the best responses that I saw was this one. We call it grip, and it let us drive fearlessly around hard corners very fast, because it will make sure that you will not mess up, right? Yeah, that's basically all I have to say. Questions?
Around using RC versus kind of the ARC, why wouldn't you just use the kind of the ARC one all the time? Is it a performance thing? Or?
Yeah, just performance thing. It's much lower than I thought. I thought it would be maybe 20% slower. No, it's maybe twice, maybe 3 times. Because my guess is that when you are using, so my guess is that you can change it atomically just by a hardware instruction or something like that. But probably in practice you need to commit to make sure that you flush your CPU cache to memory so that other threads can actually see it. And that might be the part that takes longer. I don't really know, but it's significantly slower. Other questions? No?
Thanks. Yeah, so clearly in performance-sensitive applications, this is a great fit. What about applications which are a bit less performance-sensitive, like many of the ones we have here at ITV, but are very much like about correctness? Do you see Rust as in, like, you know, where they have a lot of complex domain rules and so forth?
You have two points there. So one of them is maybe we don't need this amount of performance in our particular use case. Actually, Rust is very good at both CPU and memory. So basically, a Java application will have like this heap state, this heap space. You'll use it, and at some point we'll say, we are at about 80%. Maybe let's like stop the world and clean everything, and then we can continue. And that basically means that on the higher percentiles of latencies of your requests, you sometimes see like a huge spike because things take like 500 milliseconds because of that one time that the GC kicked in the wrong time. You don't have that here. This is very predictable because things are freed exactly in the place where they are no longer accessible. So you have a huge improvement in terms of memory. In terms of performance, maybe you are right. Maybe it doesn't matter that much because you can scale horizontally, for instance, if you can. That's fine, but it costs you dollars. For instance, Dropbox last year or 2 years ago maybe, decided to rewrite their engine, the storage engine in Rust, and they saved a bunch of money in servers because of memory that they need and because they don't need as many servers because they are faster. The other point that you said was about correctness. And yeah, I think it matters because everything that you do here is probably very highly concurrent. And many times there's no state that you actually can mess up. But if there is, this will make sure that you don't have any problem, right? So I'm almost sure that all complex concurrent programs out there have data races that just don't arise because they are very uncommon or they are benign in some way. And basically this will give that correctness for free. Also, it also gives you as a programmer a lot of guarantees. So you know that when you hold a reference, it's yours. No one else can go and change it without you knowing, right? And if you are using Scala and if you hold something and that something has stuff that can change inside of it, you don't know. Someone can change it. For instance, in Java it's very common that people, when they return something, they can just clone it because otherwise you give away to change your internal state of your class. So you don't have to worry about that. You just return a mutable reference and no one can change that for you.
Thanks.
All right, any other questions?